Let me introduce our paper titled Physics-Guided ISO Dependence Sensor Noise Modeling for Extreme Low-Light Photography, which was published at CVPR 2023. Quick preview. We investigate the noise formation process in extreme low-light scenarios and propose a novel physics-guided noise model. The ISO dependence is taken into consideration in the proposed method. Our proposed deep noise model is implemented in a normalizing flow-based framework, and 4 components are deployed to model different noises. We collect a dataset named LLD for extreme low-light image denoising. The dataset contains pairwise noisy clean images captured by 2 cameras, i.e., Sony A7S II and Nikon D850. We also provide flat field and bias frames covering a wide range of ISO settings. Introduction. Modeling imaging sensor noise poses a fundamental challenge in image processing and computer vision applications. Illustrated in this figure, an imaging sensor pipeline encompasses diverse noise sources, with each stage being susceptible to distinct types of noise. Sensor noise modeling can be categorized into 2 main approaches: physics-based statistical noise modeling and learning-based noise modeling. The existing state-of-the-art learning-based noise model, NoiseFlow, exhibits a substantial performance gap compared to the physics-based ELD noise model when simulating noise in extremely low-light scenarios, as demonstrated on datasets such as SID and ELD. Although deep neural networks excel in many vision tasks, they are inadequate for modeling extreme low-light sensor noise compared to physical model-based solutions, highlighting the need to explore the potential of learning-based sensor noise modeling. The limited low-light denoising datasets, lacking large-scale noisy clean paired data covering diverse ISO settings, impede learning-based noise modeling methods from accurately capturing ISO dependence and achieving optimal modeling performance. Our method. As shown in this table, the proposed noise model covers the most common kind of noises in the imaging process, including shot noise (shot), dark current fixed pattern noise (FP), black level error noise (BLE), dark current shot noise (DCSN), read noise (read), row noise (row), and quantization noise (Q). Besides, the ISO dependence is also better considered compared to existing methods. Considering that the shot noise, dark current shot noise, and red noise are all Gaussian distributions with the same size, we introduce a new term NHG following a heteroscedastic Gaussian distribution. Here, I represents the clean image, and D represents the corresponding noisy image. Our proposed deep noise model is implemented in a normalizing flow-based framework, and 4 components are deployed to model different noises: dark current fixed pattern noise layer, black level error noise layer, HG noise layer, and row noise layer. Normalizing flows are composed of several differentiable and bilateral mapping functions that learn a transformation x omega with parameter omega. Then the inverse transformation operation inverse can synthesize the real noise by inverse z. Equipped with real noise samples, the mapping function f can be optimized by minimizing the negative log likelihood function. We have defined our 4 layers, fully meeting the requirements of differentiable and bilateral mapping, which are inherent to the normalizing flow structure. To stabilize the training process, we adopt a 2-stage training strategy to train the proposed noise model, i.e., the random noise modeling phase and the fixed pattern noise modeling phase. After training, our noise model can be adopted in 2 noisy image synthesis schemes: clean image-based synthesis and real noise-based synthesis. Clean image-based synthesis is the most intuitive way to generate noisy images. When given enough clean images I, the corresponding synthetic noisy images D hat can be obtained. The real noise-based synthesis consists of the dark shading correction strategy proposed by PMN and the zero mean noise strategy in our noise model. We collect a dataset named LLD for extreme low-light image denoising. The dataset contains pairwise noisy clean images captured by 2 cameras, i.e., Sony A7S II and Nikon D850. We also provide flat field and bias frames covering a wide range of ISO settings. Besides, to the best of our knowledge, our LLD dataset is also the first public dataset with flat field and bias frames available for various ISO settings. Experiments. We use our noise model in 2 noisy image synthesis schemes, clean image-based and real noise-based, which are denoted by ours and ours asterisk operator. We compare our physics-guided ISO-dependent noise model with 3 learning-based methods, 3 physics-based methods, and 3 real noise-based methods. Our physical-guided ISO-related noise model, ours, can outperform ELD since we have considered the ISO dependence for black-level error noise and FPN. When evaluation on Nikon D850 camera, our model achieves the best performance. It is worth noting that PMN requires not only pairs of noisy clean images, but also a large number of bias and flatfield frames. By contrast, our method relies only on paired noisy clean data and achieves the best performance. As shown in figure, our method provides the clearest texture and most accurate color denoising result. Conclusions. We investigate the noise formation process in extreme low-light scenarios and propose a novel physics-guided noise model. The ISO dependence is taken into consideration in the proposed method. We collect a dataset for extreme low-light image denoising. The dataset contains pairwise noisy clean images captured by 2 cameras, i.e., Sony A7S II and Nikon D850. We also provide flat field and bias frames covering a wide range of ISO settings. Thank you.